Hi, my name is Ryan Nixon, and today I'm going to talk about phase, specifically what it means conceptually. So I'm sure you've heard phase lag, phase angle before, but I want to talk about what that really means to a physical system. So to start off with, we're going to start with the definition that is pretty typical for your vibrations class. And certainly applicable to many other subjects. But for vibrations, we define it as the relationship between the force acting on a system and the system's response, F, and the system's response, X. So mathematically, this is something that you can derive and have derived in your vibes class. It's a mathematical definition that is convenient for vibrations. So instead of developing these things as separate entities, we have this ratio of the response over the forcing or the excitation force, and we show it here in the imaginary versus real, so the complex plane. So here the phase angle phi is simply the angle between this vector and the real axis. So like I said, this is convenient theoretically and for solving derivations or what have you in vibrations, but conceptually it doesn't really mean a whole lot. So what does this mean conceptually? Well, phase, or phi, is actually the phase lag between the response and the excitation force. So first we're going to develop a way of looking at it that is entirely based on the fact that X and F are complex numbers. That's the only thing we know about them. So here I've written X as A plus IB, I being the imaginary number, so A is the real component, B is the imaginary component, and F also in component form with the coefficients C and D. So if I were to take this ratio, I simply get A plus IB over C plus ID. Now if I have a ratio like this, I need to rationalize the denominator because of the imaginary component. So quickly, if I take X over F, and I have A plus IB, C plus ID, the conjugate of this is simply going to be C minus ID, and I have to multiply the numerator and the denominator by this to rationalize it. So if you are multiplying two numbers like this, I find it easy to set it up like a simple multiplication problem. It just helps me keep track of everything, particularly the i's, because they're going to end up multiplying by each other and canceling out. So it's simply C times A, or AC, plus C times IB, IBC, minus IDA, and then minus I squared BD. So I squared becomes -1, and since it's negative, we get what I've written on the board here. So I just isolated the components that had the I term in it and separated them out. So if we went back to our original graph, we know that the tangent of phi is the imaginary component of this ratio over the real component of the ratio. So if I go ahead and do that, the imaginary part of X over F is just the part associated with that I. So this is just the second component in the numerator over the denominator, C squared plus D squared. The real part is just the other component. So if I plug this in, the imaginary over the real, we can see that the C squared plus D squared term is common to both, will cancel out, and you get this result. Okay, so what I've done is I've represented the phase as simply the sum of its components in complex space. So this BC minus AD over AC plus BD. So it's entirely the complex components. So now I want to represent it in a way that physically makes sense. So what I'm going to do is I'm going to represent X and F in this space as independent complex vectors instead of a ratio, as separate vectors. So in order to relate these, I'm going to need to use two different functions, the dot product and the cross product. So here I've shown just a quick synopsis of what those product rules are. So we have u dot v, and this first component, and I use bars over them to show that they're vectors. This is the magnitude of u, the magnitude of v, times the cosine of the angle between them. So here I just called it theta. In our system, it will be phi. This is the geometric interpretation of what a dot product is. The algebraic definition is actually the sum from I equals 1 to n of ai, bi. So in other words, for a two-dimensional vector, this would be a1, b1 plus a2, b2, where these are each of the components. In other words, A would be something like a1, a2, and B would be b1, b2. So that's just by definition. And then for the cross product, and notice we're just talking about the magnitude here, not the direction. So the result of a cross product is a vector. We're just thinking about the magnitude. The geometric interpretation, very similar to the cross product, except now it's just sine theta. And the algebraic interpretation is actually the result of solving for the cross product. So the cross product is the determinant of this new matrix we make with all of the ijk unit vectors. And so for u, if u is a three-dimensional vector, ux, uy, uz, vx, vy, vz, if we solve this determinant, we'll get the cross product. In our case, we're just doing a two-dimensional vector, so these uz components disappear. These are 0. And as you go through the cross product, you're left with ux vy minus uy vx. Okay, so that was just some background, little linear algebra for you to figure out how we're going to manipulate these vectors. So first, what I do is I set the geometric and the algebraic definitions equal to each other. We know they're equal. They're just different ways of describing the dot product and cross product. So you see here the magnitude of f is simply found by the Pythagorean theorem, those two complex components. And the magnitude of x, again, just from Pythagorean theorem. And like I said, phi is our angle between the two vectors. So we do this for the dot product, and we do it for the cross product. So in my case, ux, which is what I showed here in general form, ux, vx, uy, vy. Well, ux, let me move this out of the way. Ux is going to be the first component. So ux and vx will be c and a. And then uy and vy will be d and b. And then for the cross product, similarly, we can substitute those in for our system. And that's what I've done here. Okay, so now I have two equations, two equalities, using the geometric and algebraic definitions of the dot product and cross product. And what I want to do is I want to use this tangent function to describe the phase angle. So tangent is defined as sine phi over cosine phi. So if I went back and I looked at the equations I developed, so I have tangent phi equals sine over cosine. So I look at my equations, I try and find a solution for each of these that isolates the trigonometric function. So for the first one, I want to isolate cosine. So I have cosine phi equals CA plus DB, and then I divide by those two magnitudes, so C squared plus D squared, and then A squared plus B squared. And then for the next one, the cross product, I'm going to isolate sine, and I got CB minus AD over the two magnitudes again. So C squared plus D squared, A squared plus B squared. Okay, so if I took the ratio of sine over cosine, we'll see that these are going to cancel out, and I'm left with the same result. So going back to our slide, here I have the two magnitudes over each other. Those will cancel out. And what I'm left with is this BC minus AD over AC plus BD. In other words, it's the exact same solution that I had when I tried to just think of it as x over f. So what does this mean? This means that our alternative perspective is valid. It means looking at it as two independent vectors in complex space, the response x and the excitation force f, the angle between them is our phase. So we actually often think of phi or phase as omega delta t. So in other words, this is an angular lag, but we can also think of it as a time lag. So if I go to my last slide here, this is the graphical comparison. So originally, the common way we think of phase compared to the more conceptual way. So you can see here, what does phi really mean here is kind of vague, but here we can see it's simply the angle between these two vectors. So if a vector is moving in time, which is very common, then it's that lag between the two vectors, the response to an excitation force, and the lag between them. So now we can kind of think of this in a way that makes physical sense and hopefully will clarify all the problems you're having in your vibrations class. And that's all I have for phase. Thank you. Good luck on your class.